Carbon is unique because it can form compounds with many other elements, especially hydrogen. These are the basis of all organic chemistry. The simplest organic compounds are hydrocarbons, compounds that contain only carbon and hydrogen atoms. For example, methane, an alkane, is CH4 with structure H-C-H, all single bonds. Ethene, an alkene, is C2H4 with structure C equals C, at least one double bond. Key definition: alkanes equals single bonds between carbon atoms. Alkenes equals at least one C equals C double bond. So where do we get them? Crude oil? Crude oil is a mixture of many different hydrocarbons. It is a thick, black liquid found in rocks underground, extracted using drills. It is a fossil fuel formed from the remains of ancient plants and animals buried under rocks for millions of years. Other fossil fuels are natural gas and coal. Key point: these are finite, non-renewable resources. They will eventually run out. Because crude oil is a mixture, its hydrocarbons have different boiling points. We separate them using fractional distillation. Exam tip: remember, crude oil is a mixture, not a compound. We use fractional distillation because the hydrocarbons have different boiling points. Key idea: crude oil is a mixture of hydrocarbons. We use fractional distillation to separate it into useful fractions based on their different boiling points. The hydrocarbons in crude oil have different lengths, so they have different boiling points. How it works: the 6 steps. 1. Crude oil is heated in a furnace to a high temperature. 2. It turns to vapor and enters the bottom of the fractionating column. 3. The column is cooler at the top and hotter at the bottom. 4. As the vapor rises, it cools. 5. Each hydrocarbon condenses, turns back to liquid, at the level where the temperature is just below its boiling point. 6. The liquid is drawn off. The fractionating column. Hot at the bottom, cool at the top. Heated crude oil enters as vapor. Fractions come off at specific temperatures, less than 25 degrees Celsius, 25 to 60 degrees Celsius, 60 to 180 degrees Celsius, 180 to 250 degrees Celsius, 250 to 350 degrees Celsius, and greater than 350 degrees Celsius. Residue asphalt stays at the bottom. The main fractions table. 1. Refinery gases, boiling range less than 25 degrees Celsius, 1 to 4 carbon atoms. Uses: bottled gas, fuel for heating. 2. Gasoline, petrol, 25 to 60 degrees Celsius, 5 to 10 carbons. Uses: fuel for cars, making other chemicals. 3. Kerosene, paraffin, 60 to 180 degrees Celsius, 10 to 16 carbons. Uses jet fuel, paraffin heaters. 4. Diesel gas oil, 180 to 250 degrees Celsius, 14 to 20 carbons. Uses: fuel for diesel engines. 5. Fuel oil, 250 to 350 degrees Celsius, 20 to 35 carbons. Uses: fuel for ships' power stations. 6. Residue, bitumen, greater than 350 degrees Celsius, 35 plus carbons. Uses: making roads, roofing. Summary: crude oil is a mixture of hydrocarbons, mostly alkanes. We separate it using fractional distillation. Shorter chains have lower boiling points. This gives us useful fractions. Let's zoom in on the alkanes. Hydrocarbons. Definition: compounds of only carbon and hydrogen, found in crude oil, extracted from crude oil, used as fuels for heating, transport, energy. Alkanes definition: saturated hydrocarbons, only single bonds. No double or triple bonds, only CC single bonds. General formula: CnH2n+2. The alkane homologous series, methane to butane. Note: each member differs by CH2. Methane CH4, ethane C2H6, propane C3H8, butane C4H10. Properties and trends. Boiling point increases with chain length because of stronger van der Waals forces between molecules. Saturated, only single bonds. Stable, generally unreactive except during combustion. Nonpolar, insoluble in water. Uses of alkanes, fuels: methane in natural gas, butane in camping stoves, propane in LPG. Combustion: 1. Complete combustion definition: hydrocarbon plus oxygen yields carbon dioxide plus water. Happens with plenty of oxygen. Equation: CH4 plus 2, O2 yields CO2 plus 2, H2O, and C3H8 plus 5, O2 yields 3CO2 plus 4, H2O2. Incomplete combustion occurs when oxygen supply is limited. Products: carbon monoxide, CO, plus soot, carbon plus water. CO is toxic, binds to hemoglobin in blood, reduces oxygen transport, can be fatal. What is cracking? Definition: thermal decomposition, breaking large alkane into smaller, more useful molecules. Process: large hydrocarbon to smaller alkane plus alkene. For example, large chain yields small alkane plus alkene. Why do we crack? Demand for petrol and small alkenes is higher than supply. Long chain alkanes are less useful. Low demand, waxy, viscous. Crude oil contains excess large hydrocarbons. Conditions: high temperature. Catalyst is used. Steam cracking. High temperature, approximately 800 to 900 degrees Celsius. Catalytic cracking. High temperature plus catalyst. Zeolite catalyst / aluminum oxide / silica. The catalyst lowers activation energy. Products: shorter alkane plus alkene are formed. Alkenes are unsaturated, contain C equals C double bond. General formula: CnH2n. Alkenes are very reactive. Example equations. All equations are balanced. Example 1. C10H22 yields C8H18 plus C2H4. Decane yields octane plus ethene. Example 2. C12H26 yields C6H14 plus 2, C3H6. Dodecane yields hexane plus 2 times propene. Uses and test. Uses: fuels, petrol, feedstock for polymers and plastics, used to make chemicals for manufacturing. Test for alkenes. Bromine water test. Orange to colorless if alkene is present. Keywords: thermal decomposition, hydrocarbon vapor, catalyst lowers activation energy, more valuable. We use those alkenes from cracking to make polymers. 1. Addition polymerization. Definition: monomers with C equals C double bond add together. Double bond breaks. Monomers join together end to end. Forms long chain polymer. No small molecule lost. Monomer is alkene, for example, ethene. CH2 equals CH2. General equation: N open parenthesis, CH2 equals CH2. Close parenthesis yields dash open bracket CH2 dash CH2 close bracket dash N. This is poly open parenthesis ethene close parenthesis. Example: ethene yields poly open parenthesis ethene close parenthesis. Propene yields poly open parenthesis propene close parenthesis. Polythene through. Polypropene conditions: high pressure plus catalyst. Properties: non-biodegradable, unreactive / chemically inert. Keywords: monomer, polymer, long chain. Repeat unit. 2. Condensation polymerization. Definition: monomers with 2 functional groups react. Small molecule is lost, usually water, H2O, or HCl. Monomers join and elimination of water occurs. Common types: dicarboxylic acid plus diol yields polyester plus water, HOOC dash open parenthesis, CH2 close parenthesis, 4-C OOH plus HO dash CH2 dash CH2 dash OH yields dash open bracket CO dash open parenthesis, CH2 closed parenthesis, 4-COO dash CH2 dash CH2 dash O close bracket dash N plus NH2O diamine plus dicarboxylic acid yields polyamide plus water. H2N dash open parenthesis, CH2 close parenthesis, 6 dash NH2 plus HOOC dash open parenthesis, CH2 close parenthesis, 4 dash COOH yields dash NH dash open parenthesis, CH2 close parenthesis, 6 dash NH dash CO dash open parenthesis, CH2 close parenthesis, 4 dash CO dash N plus NH2O. Example: ethanediol plus hexanedioic acid yields polyester. Distinguish: needs 2 different monomers or 1 monomer with 2 functional groups. Forms ester or amide link. Ester linkage dash C O O dash amide linkage dash C O N H dash natural condensation. Polymers D Na to nucleotides join via condensation. Phosphate ester link. Proteins: amino acids join via amide peptide link. Comparison table: addition versus condensation feature. Addition, condensation monomer type. Alkene, contains C=C double bond, monomer with 2 functional groups. Functional groups, C=C double bond only, 2 functional groups, e.g., COOH and OH, COOH and NH, 2 product. Polymer, no loss of small molecule. Polymer plus small molecule byproduct. None, water, H2O or HCl. Lost link type, carbon-carbon chain, ester linkage-C. OO- or amide linkage-C. ONH-. Example, ethene to polyethene. Ethanadiol plus hexanedioic acid to polyester. Keywords: monomer, polymer, ester linkage, amide linkage, elimination of water, biodegradable options. Condensation polymers can be biodegradable, important for sustainable materials. What are polymers? Definition: a polymer is a long-chain molecule made from many repeating monomers joined together. Monomer starts ends. Monomers are small molecules that join to form the long polymer chain. The repeat unit is shown. A. Addition polymers and uses. Formed from alkenes, molecules with C=C double bond. Examples: polyethene, from ethane C, H2=CH2 yields, open bracket CH2-CH2, close bracket -N polypropene, from propone C, H2=C, H-C, H3 yields open bracket C, H2-C, H open parenthesis, C, H3 close bracket -N polychloroethene /PVC, from chloroethene C, H2=C, HC. L yields open bracket C, H2-C, HCl close bracket -N bullet, uses plastic bags, packaging, bottles, cling film bullet properties, strong, low density, unreactive, non-biodegradable B. Condensation polymers and uses. Formed by condensation, monomers join and water is eliminated. Polyester, for example, PET from dicarboxylic acid plus diol yields ester linkage. Uses drinks bottles, clothing, fibers, plastic bags, packaging, cling film, water pipes, insulation, cables, foam. PET bottles are an example. Polyamide, for example, nylon from diamine plus dicarboxylic acid yields amide linkage -CONH- yields nylon. Uses clothing, ropes, parachutes, tents. Condensation releases H2O as byproduct. C. Thermosoftening versus thermosetting. Thermosoftening. Weak intermolecular forces between polymer chains. Soften when heated, can be melted and reshaped. Can be remelted and recycled. Examples: polyethene, PVC. Thermosetting. Strong covalent cross links between chains. Do not soften when heated. Remains rigid. Do not melt. Do not recycle. Examples: bakelite, epoxy resins, resistant to heat. D. Natural polymers and environmental issues and recycling. Natural polymers. DNA, genetic material made of nucleotides. Proteins, made from amino acids. For example, enzymes, hair. Starch, energy store in plants, made of glucose. Cellulose, cell walls in plants, made of glucose. Environmental issues and recycling. Non-biodegradable, builds up in landfill. Microplastics, tiny fragments pollute oceans, harm wildlife. Burning leads to produces toxic gases. CO2, HCl from PVC leads to air pollution, combustion issues. Recycling reduces waste and reduces use of crude oil. Life cycle assessment, LCA, evaluates environmental impact from raw materials to disposal. Key message: polymers are strong, durable, and useful, but we must recycle and manage waste to protect the environment. Life cycle assessment, LCA, a method to evaluate the environmental impact of a product throughout its whole life cycle. LCA, 4 stages. 1. Raw materials, extraction, mining, quarrying, harvesting raw materials. Crude oil is a finite resource. 2. Manufacturing, processing into the product, energy and water used, pollution from factories. 3. Use, product used by consumer, energy and water used during use, emissions/pollution during use. 4. Disposal, end of life, landfill, incineration, recycling, reuse, waste produced. What LCA evaluates: energy use, water use, pollution, air, water, land, resources use, waste produced, carbon footprint uses of LCA, comparing products. For example, plastic bag versus paper bag arrow, data availability which has lower impact. Keywords: LCA, carbon footprint, crude oil, finite, pollution, sustainability, biodegradable, photodegradable. Waste disposal methods. 1. Landfill pros. Cheap, simple cons. Land use, takes up space, produces methane, a greenhouse gas. Leachate can pollute water/groundwater. Non-biodegradable waste persists. 2. Incineration pros. Burns waste to reduces landfill volume, generates energy from waste. Cons. Produces CO2, greenhouse gas 3. Recycling pros. Reduces need for raw materials, saves resources and energy compared to producing new, reduces landfill waste. Cons. Energy cost for collection and sorting. Not all materials recyclable. Recycling process uses energy. Polymers, recycling notes. Thermosoftening polymers contain no cross-links, soften when heated, can be remelted, reshaped, recycled, sort clean, and melt when heated. For example, PET materials, recycle/UV PET. 4. Reuse pros. Extends life of product, reduces waste, saves resources and energy. Cons. May need cleaning/storage, not always practical. Comparison table. Waste disposal methods. Pros and cons methods. Some pros, cons. Landfill, cheap, simple, widely used. Produces CO2, GHG. Toxic gases, for example. HCl from PVC, ash waste. Incineration. Reduces landfill volume, generates energy. Air pollution recycling. Saves raw materials, saves energy. Reduces landfill. Energy needed for collecting/sorting. Costs/time. Reuse extends product life, saves resources and energy, reduces waste, may need cleaning/storage. Not always possible sustainable development, meeting present needs without compromising future. GCSE tip. LCA helps compare the overall environmental impact of products. Remember, no option is perfect.